So I'm repeating myself because I wasn't kidding when I said if you understand this, this explains everything we're doing for about the next month and a half. The 3 laws of static charge, you can fill this in. Like charges repel. Right? You have that in your notes. What's the next one? Unlike charges. And then the third one is a bit, so this is right in your notes, right? Like charges repel, blank. It says blank charges blank. And then it says blank charges, so unlike charges attract. And then the third one is a bit more obscure. Neutral charges are attracted to anything that's charged. Basically, if objects repel each other, you know they're charged the same. If they attract each other, they might be opposite, they might be neutral. Really, if they attract each other pretty strongly, they're probably opposite. If they attract each other mildly, probably one of the objects is neutral and the other object is charged. What we want to talk about today, Rihanna, is what it is exactly that's doing the attracting or the repelling. And the answer in one word in physics is it's a force. But we need to talk about what types of forces there are. So there are 2 types of forces. The first type is what we call a contact force. And for a contact force, the object must be touching. Let me give you a good example of a contact force. These are the most common forces. Hey, as an example, a person pushes or pulls an object. But then, for several hundred years, scientists recognized that there was a second type of a force, and they called it action at a distance forces. And that's a fancy way of saying somehow I'm causing an object to move, but there's air between us, space between us. Again, think last class with the electroscopes. As you brought the rod in close to the electroscopes, you made the foil move apart without actually touching the metal on the top yet. There was a gap. So, action at a distance forces. This, unless we can find an explanation, is witchcraft. Because this allows somebody, for example, to be able to lift something with their mind. It allows the X-Men and all that stuff to be true. If you somehow allow a force to be applied on an object without touching it, unless you can explain it, you have to allow for magic and witchcraft. So we're going to try to explain it. This acts on an object without touching it. And I'm going to contradict myself shortly, because I'm a physics nerd, and I think the textbook is actually making a mistake. As an example, electric forces. 2 positive objects can repel each other, but there's no contact. You saw the other day, for example, I charged up, I think it was a plastic ruler, and it was able to pick pieces of paper up, and in fact the pieces of paper, when there was still a small gap between the ruler and the paper, leapt up. They jumped up. I applied a force to that paper without actually touching it. So it can be a repulsion or it can be an attractive force.
What can you do with your hands? So if you want to take on your hand, then you can do it with paper.
My hand doesn't have a good ability to deposit electrons. It's reasonably good at attracting electrons, but human skin is not all that conductive. In fact, in Physics 12, we actually crunch the numbers, and we show that you can actually, it takes a fair bit before the current will go through your skin and into your body, but once it gets into your body, inside you're mostly water, mostly salty water, which is conductive, and that's why you can take a good shock without getting damaged, but once it penetrates your skin, it can cause your heart to fibrillate, and that's how you die from electric shock. 2 other action at a distance forces, magnets and gravity. I'm going to assume you've all played with magnets, and you've seen when they're close together, all of a sudden they'll leap towards each other and connect, even though they weren't touching to begin with. How? This is what Michael Faraday, one of my favorite scientists who lived in the, well, about 1830 to 1880, and also basically invented most of our electrical system. He invented the generator, he invented the electric motor, good scientist. He said, they are touching, but they're touching invisibly. The objects exerting the force send out an invisible field. In this case, an electric field. For magnets, a magnetic field. For planets, a gravitational field. He said, actually, there's no difference between me whomping Aiden with a baseball bat and causing two objects to move towards or away from each other with an electric field. The baseball bat was what I used to apply the force. The electric field applies the force. The only difference is, an electric field, it's invisible. That's all. Which may still sound like magic and witchcraft, but it's less creepy because it's saying there is something there. Our eyes just can't see it because our eyes don't have the ability to see that particular frequency of light or whatever. We can't see it, but we can measure it. We know it's there. I wrote down here, oh, Mr. Dueck's field rant. Not on test, but cool. So, electric fields, I'm not going to ask you this, but fields in general are kind of cool. Let me pause the video. End of field rant. So, I have here the charges and electric fields simulator. Put your pencils down, look up. Okay? I'm going to take a positive charge. Yunk. Put it right there. What you can't see is that it's sending out an electric field. If you could, you would see something like that. And as you got further and further away, it gets weaker and weaker and weaker. Then, if I put a negative charge in, what will the positive and the negative charge do to each other? Attract or repel? Attract. And you can all of a sudden see the electric field of the positive charge bends, curves, is attracted towards the negative, and they're pulling on each other. It's invisible, I realize that, but it is there. That's what's applying the force. In fact, I even have electric field sensors. Right here, it's really strong. Very strong close to the charge. As I go further away, the electric field gets weaker and weaker and weaker and weaker, but again, as you get closer, it gets stronger and stronger and stronger and stronger. Heck, I can even, I think, show numbers. Add a grid. We can even bring in voltage, but that's another show. Turns out, believe it or not, this is how radio works. How many of you have listened to the radio before? Only one of you has listened to the radio before? How many of you understand how the sound, how the signal gets from Vancouver to here? It's really quite simple. Put your pencils down. You don't need to know this, but I can't resist showing you. Okay? Basically, because electric fields go out to infinity, go out forever, you can send information by wiggling an electric field. So here is the radio station, and they send a changing electric field. It says wiggle the electron. And that goes out forever and ever and ever, and then you have a corresponding antenna that, if I make this a little bigger, detects those changes, and you should see in the antenna a very, very small amount of wiggling. You know what? Let's go like this. We'll make it oscillate on its own. There you go. And your radio then translates this back into sound. It's much more complicated than this because the signal itself is a signal on top of a signal on top of a signal on top of it. It's got multiple waves. But this is how we can use electric fields, because they go out to the edge of the universe, to pass information. Radio waves. Let's see. Oh, electric field. There's the electric field going up and down, oscillating. Heck, let's change the frequency. By the way, frequency, F, one way to do it is to modulate the frequency. That's FM. FM stands for frequency modulated. AM radio, they don't modulate the frequency, they modulate the amplitude. AM stands for amplitude modulated. And those are the difference between the two bands. Do you need to know that? No, but nerd trivia. That's how gravity works. Goes out in all directions. So this is my field rant, not on the test, but cool. Turn the page. This is on the test. Add the appropriate force arrows. So in the top, I gave you 3 diagrams. In the top diagram, what kind of a force would the positive feel? Hang on one second. So this is a good test question that I don't mind asking. Look at this positive and this negative. Temporarily ignore those guys. Don't scribble them out on yours, but they're not part of the diagram. Which way will this positive feel a force because of this negative? And we're going to use our 3 rules. Like charges repel, unlike charges attract, neutral charges are attracted to both. So this positive, will it be attracted or will it be repelled by that negative? So it's going to feel a force tugging it that way. Draw that in, please. What about this negative? Will it be attracted or repelled to the positive? It's going to feel a force that way. So can you make a prediction? If those 2 charges were free to move, how would they move? Away from each other or towards each other? Towards each other. What about this drawing here? This positive, which way will it feel a force because of that positive? What about this positive, the right-hand positive? Which way will it feel a force? Okay, these would repel. What about if I had those 2 negative charges sitting right there? How will they feel a force? I think the same way. They'll repel each other. Aiden quietly said, like magnets. Well, it turns out we learned around 1880 that magnetism and electricity are 2 sides of the same coin. In fact, we call them electromagnetism. They're different aspects of one big uber phenomena, it turns out. I'm not saying magnetism and electricity are the same thing. I'm saying they're symptoms of the same bigger thing. Oh yeah, for you guys, turn the page. So, these are some questions I might ask you on a test. Let's do some reasoning. Let's suppose you had more charge, more positives or more negatives. Do you think that would make this force bigger, smaller, or stay the same? Taya. Bigger. More charge equals more force. So if I want to increase the force that one object feels, I can add more charge. What if I increased, you got to fill in that first blank, the distance? What if I moved them further apart from each other? Do you think that they would exert a bigger force or a smaller force? Based on the few electric experiments that you've done so far, have you noticed that the force is stronger when you're closer, or is the force stronger when you're further? So if you increase the distance, what would happen to the electric force between the 2 charged objects? Bigger, smaller, stays the same? Okay, let's come back to that. Heck, if you decreased, if you move them closer together, do you think they'd feel a bigger force, a smaller force, or the same force? As you move them closer together, they're going to feel a stronger, well, if they feel a stronger force when you move them closer together, what do you think they feel if you move them further apart? Weaker or less. Okay? Give you an example. So let's do an example. Oh, here's the answer. More charge, stronger or bigger force. Increased distance, reduced or weaker force. Decreased distance, increased or stronger, whatever word you want to use. Bigger force. Psst. Put that away, please. Oh, is that a calculator? I'm sorry. Thought it was a phone. My bad. Can you bring the two south poles of two strong magnets together? Have you ever tried taking two strong magnets and set them up so that they're repelling each other and actually then tried to bring them together? You can't. It always, when you get really, really close, pushes you off. Pushes you off. The closer you get, the more strongly they repel. That's for magnets, but that's because that's how fields work. The closer you get, the more strongly they'll repel or attract. That's for electric charges. In fact, it goes back to this diagram here. Oh, I still have charges and fields open. Let me clear all. So here's my charge. If I want to measure the electric field strength, it's fairly weak here. As I move closer, should the electric field or the electric force get bigger, smaller, or stay the same? See it? In fact, when I get really close, it gets really, 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 really big. Okay? We already did the electroscopes lab. Turns out there are two main methods of charging objects, and you're going to need to know these words. By conduction, putting a box around it because I'm going to ask you these words, and by induction. You can charge by conduction. You can charge by induction. Let's talk about charging by conduction. When a negatively charged insulator touches a neutral object, the electrons flow into the neutral object, giving it a charge. When a negatively charged insulator touches a neutral object, the electrons flow into the neutral object, giving it a charge. Remember the electroscope? You made the rod negative, then you touched the electroscope, the leaves moved apart, and they stayed that way when you moved the rod away. In fact, Mateo stayed that way for a few hours. There's a lovely picture. And we have physical contact right there. That's conduction. Conduction needs contact. Hey, you know what? That's so good that I should probably have that in the notes. Oh yeah, there it is. Conduction. Contact. You're not foolishly texting or anything, are you? Talking to somebody else, but thanks for feeling guilty. What would happen if you touched a neutral electroscope with a positively charged object? Let's see. Let's see if we can kind of visualize here. So normally we have an electroscope. There's the knob. I'm not going to draw the big jar container. We have these foil leaves, and I'll draw them basically dangling down. And you're going to bring a positively charged object in. I want you to just watch. We're going to draw some later. And we're going to touch it. So in fact, I'm going to draw this positively charged object touching. Now, right now, Aiden, these foil leaves are neutrally charged. I'm going to put 3 negatives and 3 positives on each one to show they're neutral, even though it's trillions of negatives and trillions of positives. What's the charge on this rod? What's the charge on this rod? So what will the electrons here do? Where will they want to go, Jordan?
To the positive, the top, whatever that is.
The positive,
Yeah.
the little rod. Okay, so you know what? Some of these electrons, I mean, a few will stick around, but some of them will end up going here because they want to go to that rod because it's positive, and unlike charges are attracted. But of course, as soon as they do that, Aiden, look at what used to be neutral. What's the charge on those foil leaves now? Overall positive. Are they both positive?
Yeah.
So what will they do?
Repel.
Repel. The same as actually when you touched it with a negative. When you touched it with a negative, what happened was extra electrons flowed from the rod into the leaves and repelled each other. When you touch it with a positive, extra electrons flow from the leaves into the rod, leaving the leaves positive, still repel each other. So it says discuss with your partner, then discuss with the group. We just did. So same result. You don't need to write this down. But you do want to write down conduction needs contact. And then I'm going to give you a situation here. It says this. A negative rod is brought close to an insulating ball. The ball is first attracted and then repelled by the rod. Really? Yep. In fact, this might make a nice test written question, drawing this picture. So here's the pictures that I have. There's the rod and there's the ball. This is my high-tech stick figure diagrams. This is about as good as I am on the graphics. You can put your phone face down because you're not that important, Jordan. Thank you. What was the charge on the rod? What was the charge on the rod? Negative. So I'll show that. Let's go minus, 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 minus. And you know what? Just to remind us, put a couple of pluses on there. Because when we're saying something's negative, we're not saying it has no positives. We're saying it just has extra negatives. What was the charge on the ball? Neutral. How would I draw that? I'll go a plus and a minus. Now, really, it's trillions of pluses and trillions of minuses, but they're the same charge. Yep. Pardon me? I think I am. Yep. Thanks for being concerned. Now we touch. What happened that splits? And you saw it was almost instant. It was bing, and then so conduction doesn't take very long. What happened? So now it's going to be negative, 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 still a plus. Let's just put some extra negatives on the ball. And this is still negatively charged because not all of the extra electrons were able to flow. It happened so fast. Which means this is negatively charged and this is negatively charged. So now they are like charged. What happens? What do like charges do? Repel. You can cross that diagram out. I don't think I need that. Repel. Gonna make it, Youngjun? Yeah, writing this down? I don't think you are. Okay. Turn the page. What would happen if you brought a charged object close to the knob of an electroscope without actually touching it? Well, we did this experiment, but for those of you that were away, we'll show you. When you brought the rod in close without touching, what did the leaves do? So clearly you've somehow managed to charge something, but you haven't touched it. This is induction. Got a video and a cool toy to show you. Put your pencils down. So I wrote here, Mr. Dueck has a pretty cool electric wand toy. Do you understand the physics of what was going on there? We were charging the wand, and because the mylar metal was also touching the wand, it was conducting, it was picking up extra charges, and eventually you ended up with two like-charged objects. In this case, I know they're negatively charged. Oh, and what do like charges do? Repel. Okay? Charging by induction. Pick your pencils up. charging by induction. One way to do this is where charges in a neutral object are temporarily moved away from a charged object, but they then return when the charge is removed. There is a way to make this permanent and not temporary, but I'll show you the temporary way. I wrote down here, balloons and static electricity sim. I showed you this one already. But we'll look at it again. This explains why when we rub the balloon on Nicole's sweater, here's Nicole's sweater, the wall is neutrally charged. See the yellow wall? It's neutral, but can you see as I come close what's happening to the charges in the wall? We are able to charge the, for you guys, the left side of the wall, the outside of the wall, positive, and the inside of the wall becomes negative. Have we touched the wall yet? No. This is charging by induction. Now, it's temporary because when I move the balloon away, what happens? They spread out and go back neutral. So that's one way to charge by induction. There is a way to do this permanently. And they're really, in fact, how many of you have an electric toothbrush? So your electric toothbrush charges by induction, not conduction, because we don't want pieces of metal attached to electricity around a bathroom sink. That would be bad safety. So they charge through what's called an induction charger. They're talking about putting those in phones in the next generation of phones. What they want the next generation of phones to be, instead of plugging it in, you just lay the phone down on a charging pad, and the pad charges it without actually having to plug in a cord through induction. How? Well, here's one way. It says this: two uncharged or neutral metal spheres are fixed onto supports and are touching. A charged negative rod is brought in close to the spheres. With the rod still in place, the spheres are separated. The rod is then removed. What happens? You ready? Here's pictures. Let me make this a little bit bigger. Okay. Starting out, we have two metal spheres, and they're touching each other. Are they neutral? Yeah. How can I tell? Two positives and two negatives on each one. That was my high tech. Now, I'm going to charge this rod negatively. So can you draw in negatives? Okay. What's going to happen in these two metal spheres? What will these negatives do? You're right. Repel what? Which charges? In fact, what's going to happen, I think, is the negatives are going to move as far away as possible, and the positives are going to move as close as possible. Now, overall, Lexi, both spheres are still neutral because they both still have 4 plus and 4 minus. However, keeping this rod here, now what I'm going to do is I'm going to slide this sphere to the right. I'm going to touch the bottom. I'm going to slide it apart. The positives would stay there. The negatives would stay there. You see that okay, Dan? And then if I remove the rod out of the picture, I end up with this. Did I touch the spheres? I'll come back to it. Did I touch the spheres? No. But was I able to charge them? Yep, that's charging by induction. And this one's permanent. Okay? If you scale that up and you add some cleverness, Kiana, this is how your electric toothbrushes have an induction charger inside. There's no actual contact between metal. There's no conduction. It's induction because it's safer. Induction is indirect. If you're looking for ways to keep them straight. Conduction requires contact. Induction is indirect, no contact. Okay. Nice yawn. I know I've been talking most of the class. I want to finish off the lesson today, and then Thursday is going to be a take-home quiz and a work period and kind of review. And when did I say your test is? A week from Thursday, so that way we can have review and study and all that. So I know you guys have been patient, although I've given you lots of mini breaks with videos and toys and stuff too. So suck it up. 15 more minutes. I hope I can get it done in about 8. Okay, you figured that out okay? Uh-huh. Need applications of static charge. Photocopiers. Now I wrote here, see page 261 in your text. If you have a textbook, you can look at page 261, but I also have a copy that I'll beam up here as well. Let me pause. So need applications, Nicole? Photocopiers. Kind of cool. I wrote down here, reading check, page 262, numbers 1 to 5. Turn to your lab partner and ask yourself the following questions. Now, if you don't have your textbook here, I'll make this nice and big. So turn to the person next to you, and I think everyone has someone next to them except for Aiden. So Aiden's going to ask, I'm going to ask Aiden, oh, yeah, I'm going to ask Aiden the questions myself. Take about 5 minutes. So, folks, I'm not wild about every one of these questions. In hindsight, I should have crossed some of these out. But certainly, you absolutely need to know number 3. And you need to know, for number 4, further apart, weaker force, closer, stronger force. Stop looking at your phone, whoever that is. Lena? Put it away. Okay.
Whoa.
So, I think we're nearly done. We are. Attraction of neutral objects. A negatively charged balloon will stick to a wall because the electrons in the wall move away from the balloon, creating a charged area on the wall. A negatively charged balloon will stick to a wall because the electrons in the wall move away from the balloon, creating a positively charged area on the wall. Like that. Yeah, he doesn't look too thrilled. Okay. Show that later. So what's your homework? I want you to finish off the Bill Nye stuff from last day. And if you haven't finished the section, guys, if you haven't finished section 7.1, finish that. I'm going to hand this out tomorrow, well, Thursday. Okay? So your homework is finish Bill Nye.